Okay. Okay, so let's do some review a bit. So we've been discussing on the Daniell cell. So let's look at this Daniell cell sketch. So you have the anode, which is always represented on the left, and you have the cathode on the right. So the anode is zinc. So the way to normally write this, is you have the as a notation the zinc as the anode. So you have the zinc metal, and there's a straight one line here that indicates different phase, and this is the electrolyte phase, zinc 2 plus and aqueous, and you have the bridge noted by the double line, and on the other side then you have copper 2 plus electrolyte aqueous, and there's one line that separate the electrolyte phase and the solid phase, right? So this is the notation. So if you look at the zinc, right, you have the zinc metal plate here dipped into a zinc containing solution, right? There is some zinc 2 plus here. So the moment you dip it under standard half cell conditions, right, so there will be some amount of zinc metal, that a very small amount of zinc metal that gets oxidized and becomes zinc ion here, and the electrons is left on the surface, right? Really small amount. It's small. It's small, but it's enough to generate some negative charge on the zinc surface, right? The opposite case happens on the copper surface, on the cathode. When you dip copper in a solution containing copper 2 plus, there will be an electrical potential difference between copper solid plate here and the electrolyte, and this happens because for copper some amount of the copper 2 plus in the electrolyte solution will be deposited, and will be deposited on the copper, will be reduced and thus deposited on the copper metal, and then it will generate a positive charge, right? So because you are using the electrons in the copper metal to reduce copper 2 plus, and there will be an excess of positive charge, more positive than this one. Because of this potential difference, we see build up in the potential here in the voltmeter. Okay, so if we look at the reaction taking place in the anode, or on the left, you will have zinc dissociating or go oxidized into zinc 2 plus and 2 electron. On the cathode side, you will get the copper 2 plus being reduced into copper metal, right? So each of this system has its own half cell potential, right? For copper is around copper is 0.34, exactly correct, from the table, and zinc is minus 0.76 volt. Okay, now the E naught cell is the E cathode naught minus the E anode. Now if you do this, you take the value directly from the table. The table is presented as reduction table, so the E cathode is 0.34 minus, for the E anode, minus 0.76, so that will give you 1.1 volt. Okay, so if you go back to the half cell reactions here, right, so the net reaction would be zinc solid plus copper 2 plus going to zinc 2 plus plus copper solid. Okay, so we're continuing the Daniell cell discussion. So just to repeat, we have this anode and cathode half cell reactions. The anode is always oxidation, and cathode is the reduction, right? So the net reaction for the Daniell cell is this one with the E naught of the cell that you calculate directly from the potential in the table to be 1.1 volt. So this 1.1 volt, you can convert it directly with this formula for the Gibbs free energy of reaction at standard condition, because you have the naught here. So F is a Faraday constant, 96485 coulomb per mole. 2 N here is the number of electrons participating in the oxidation reduction reaction, which is 2, and E naught of the cell is 1.1. So the calculation gives 212,267 joule per mole, or 212.3 kilojoule per mole. That's the Gibbs free energy that you can take if you do this reaction at standard conditions. Now, the standard condition means can also give you the equilibrium constant, right? So remember this formula: delta Gibbs free energy of the reaction at standard condition, delta GR naught, is equal to minus RTO1K. R is gas constant, T is the temperature, and you can plug this value here. Let's substitute that. So in principle, if you know the E cell and you know the N, the number of electrons participating in the reaction, you can calculate K. And for the Daniell cell at 298.15 Kelvin, this K is about 1.55 times 10 to the power 37. Which means, well, first of all, we have to know what K is. So let's calculate K. For this reaction is activity of zinc 2 plus times the activity of copper solid, that's the product, over the sum of the reaction, the reactant, the activity of zinc solid times the activity of copper 2 plus, right? And this is this value. So this means that the reaction, if you take the energy, if you use the energy of this battery, the reaction will proceed to the right until it has reached this value of equilibrium, or it has reached the activity ratios of this value, and then the reaction will stop, right? Because it has reached equilibrium. All right. So, okay. Now, you, if you are at E naught of the cell, for Daniell cell, it's 1.1 volt. This is at standard condition. And this will give you the Gibbs free energy at standard conditions. But what happens if you're not at standard conditions? What if not at standard conditions? Okay, so then the measured E of the cell will not be the same as the E naught of the cell, right? There will be some changes, and that changes is a function of the concentration of the reactant and the product. That's okay. This is E of the cell. So we can derive it from the Gibbs free energy. If you're not at standard condition, then the Gibbs free energy change of the reaction is equal to delta GR naught plus RT ln Q. Now what is Q? Now Q is also the same, the way you calculate it is the same as K. So for the Daniell cell is the activity of the product over the activity of the reactant, right? So Q is not the same as K, right? So by using this relation, you can convert this delta GR into E. So if I divide all of this with minus NF, right? minus NF. Okay, then this will give me E naught of the cell from this equation, right? And this would give me RT NF ln Q, and this will give me E of the cell, right? So this tells me that if I'm not at standard condition, right? If I'm not at standard condition, then the E of the cell that I will read from my voltmeter will be a function of the E naught of the cell minus RT over NF times ln Q, right? Remember, at standard condition, all the activities are 1 at 298.15 Kelvin. All the activities are 1, right? This is 1, 1, 1, 1. So if you're not at standard condition, so this value will not be 1. Okay? All right. This equation here is called the Nernst equation. Great. It tells you, it helps you to predict what will be the E cell of your system when it's not at standard condition, right?